Hey there, John Wolfe with Maile Technical.
Hi, Alasdar Mullarney, John's co-conspirator at Maile.
Alasdar and I are going to talk about modeling and time. But before we do, I have a little confession to make. I'm really bad at talking to a camera. And when I started reviewing some of the early stuff that I shot, I thought, man, am I this bad in front of a live audience? I thought, oh, well, that's it. I just need an audience. Well, when Jana mumbled something about prior commitments, Ella agreed to step in. So I have a live audience, and we'll see how all this works. So you may remember what Steve and Sally said in this book about time. But just so that we're all on the same page, let's do a quick review of two aspects mentioned in the book: access to a real-time clock and delayed events. First, let's cover real-time clock. So access to a real-time clock basically means that your models can get access to the current date and time whenever they need it. Because some applications need to know when a certain date or time arrives so that they can do something appropriate, like shut down the power grid for the entire planet. Other applications don't really care about certain dates and times, but they need the ability to measure elapsed time between two incidents, two things that happen in and around the system, like maybe the start and end of a presentation. As Bridgepoint users, we get bridge operations provided by the architecture that allow us to retrieve the current date and the time whenever we need them. These are just basically synchronous services provided by the architecture. And the implementation varies from one platform to the next, but they all do basically the same thing. So if you're still awake at this point, use the chat to share an amusing story with us about how you've used a real-time clock in models that you've built in the past.
So we have synchronous retrieval of time and date information covered. That's sufficient for me to model the time clock that I used to punch in and out as an engineering student when I spent a summer at the Irish Railway Engineering Works. Work experience, it was called. Every morning, I would stick my card in the slot in the time clock, and it would print the time. An example of a simple application showing instantaneous response to an external input. By the way, that clock wasn't entirely dumb. It knew enough to print the time in red if I was even 5 minutes late. And that allowed some clerk in the payroll office to deduct 15 minutes from my pay. However, synchronous response is really not enough for the more interesting applications. Who has never come across some version of "you have been logged out due to inactivity"? To accomplish this, the application must have a means of determining that some measure of time has passed. Polling, did I hear? Oh no. Surely what we want is an active, asynchronous response. This is where delayed events come in. An activity can send an event to a state machine specifying a delay duration from now. Understanding that we have the capability to trigger responses at determined times in the future, let's explore the possibilities that open up and the implication on testing our applications. Who has the best war story concerning delayed events? Surely we all have a few. Access to a real-time clock and the ability to send delayed events allows us to build all sorts of interesting real-time applications, but testing them may be another matter. Some applications may take a long time, as in hours, days, even weeks. Some time back, I worked with John on an autopilot for a stratospheric balloon. The autopilot's task was to maintain a commanded altitude within some limits by deftly manipulating a compressor and a vent valve on the ballast tank. But when the balloon was transitioning between commanded altitudes, the control policy was not really in effect, and that could take hours. So monitoring a real-time test could get quite boring. You don't mind watching the balloon for a few hours? We recently built a simplistic client-server payroll application as a proof of concept for a client who was interested in xtUML. Nothing of interest happens until the 13th of each month. Then there's a flurry of deadlines for approval, review, submittal to finance by the 15th. Discrete event simulation points us towards a useful technique. Instead of strictly tying our execution to the real-time clock, we allow the application to fast forward during periods where nothing interesting is happening. This allows us to run a potentially long scenario in quite a short time while preserving the correct ordering of events. The implementation is quite straightforward. When all of the events that are scheduled at the current time, as seen by the application, have been processed, instead of patiently waiting for the next most imminent timer to expire, we simply advance the simulated time to the expiration time of that timer. This approach is supported by a configuration switch in the model interpreter we use for testing and by marking in the various model compilers that we use.
Okay, so we can use simulated time to speed up testing of systems that would otherwise take way too long to test in real time. So now let's talk about the other end of the spectrum. Let's talk about systems that have sub-second timing requirements. Alasdar and I prefer to do most of our testing on a development host rather than target hardware. We typically build model test benches that include models of peripherals and the environment, the things in and around the system, so that we can focus our effort on the application that we're testing. And we do a lot of this testing with a model interpreter because it provides great visibility into the models. It's really convenient, and basically because we're lazy. Remember the balloon autopilot that Alasdar mentioned? In addition to taking a really long time to do anything interesting, this thing has some millisecond timing requirements for interactions with its two primary actuators. There's a compressor that pumps air from the exceedingly thin surrounding atmosphere into a really delicate balloon known as the ballast tank. There's also a vent valve for releasing air from that tank. Add air to the ballast tank, and the balloon goes down. Release air from that ballast tank, and the balloon goes up. So the autopilot must ensure that the actuator is actually doing what they're told to. And it uses timers set for a few milliseconds to monitor those actuators and ensure that they're doing what they're told. Because if the actuators aren't doing what they're told, we can easily overpressurize that really delicate ballast tank to the point of exploding it. Or we can accidentally dump all of that precious air from the ballast tank, sending the entire craft on a rapid ascent beyond the burst altitude for the lift bullet. Either of these failures sends that 1,000-pound payload hurtling toward my neighborhood. Even though an interpreter is really convenient, it executes models much more slowly than generated code. So consider how this might work with a system that has durations of timers measured in milliseconds or microseconds. Basically, it doesn't. Running an interpreter means that the processing time is significant relative to the duration of the timers when we're talking about timers in milliseconds and microseconds. So we end up with timers that fire before the modeled application in its test bench can do anything useful. And the end result is an autopilot that always thinks its actuators have failed. It turns out that the same simulated time solution for speeding up slow-running, boring applications that take way too long to test in real time works really well for testing applications with sub-second durations on their timers when you're running on an interpreter. So think about that for a minute, and I'm interested, who can tell us why this is? We're going to move on and leave that question hanging because I want to see the answers from the audience, at least those of you who are awake. Since simulated time solves both these problems, maybe we should do all of our testing with simulated time enabled. And indeed, for most automated testing, simulated time is often the best choice, as it minimizes the time required to execute a long-running test suite.
But for interactive testing and demonstration, using simulated time may not be appropriate. Consider an application that includes timeouts for interactions with humans. If we're running with simulated time, these timeouts would expire long before a human could interact with the system. And also consider that not all testing is to verify expected outcomes. We may be offering a preliminary implementation to a client for acceptance testing. What would you like to see changed? Ideally, we would like a mix of simulated time and real time. Simulated time to get to the next interesting action, then real time to explore that interaction. More on this later. Interestingly, we can build models that simulate the actors that interact with our system under test. And by configuring these models to play out different scenarios, we can build test benches that host test suites that exercise a number of different scenarios entirely in simulated time. This is most useful for regression testing. Are any of you in the audience using similar techniques?
And now for something completely different. Some applications store dates and times and calculate durations, and we want to explain how we're doing that in our models. Clive wanted an example, mainly for education and demonstration purposes, and he was already using a requirements specification for a car park control system. He was using this for some other classes that he runs at the university. So we decided we would go ahead and build a model of this car park control system. And to make it easy to store date and time and compute duration, we use an epoch-based time system, similar to those that you find provided by many operating systems, including all of the Unix-based systems. So the bridge operations that I mentioned earlier for retrieving the current date and time simply return either the number of seconds or the number of microseconds since the beginning of the epoch. Storing dates and times and calculating durations is then pretty simple because you're just dealing with integers. These numeric values representing specific points in time can be formatted for human consumption whenever you need to, using yet another bridge operation. This epoch-based approach is pretty common, and we're wondering whether you're using other techniques to do the same thing. Certainly, if you've found something better, let us know in the chat.
Now, consider how we might live test or demonstrate an application like the car park control system that John mentioned. We could arrange a scenario where the vehicle enters the car park. Then we go find something else to do for a few hours, play a video game perhaps. And eventually we get to monitor the car's exit and check that the calculated fee is correct. Perhaps there is a better way. Suppose we arrange to manipulate the time base as seen by the application. Our developer can then spend more time testing and waste a little less time video gaming. Consider the following scenario. The vehicle enters the car park at 7:42 a.m. 5 hours later, the patron pays at the pay station, mindful of the 30 seconds timeout. A few minutes later, he exits the car park safely within the allowed time. And we check that the calculated fee is $34.
Supporting this test case requires two capabilities. We need to set the time, as seen by the application, to an absolute time. And we need to advance the current time by a duration. To do this, we just need
to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts!
This is a video of the code generated from the modeled car park control system running on my development host. We use handwritten clients to simulate the entry and exit stands, the payment machine, and operator consoles. And we use a similar client to manipulate the time base as seen by the modeled application. So you'll see in this video that we first set the time to 7:42 a.m. before sending a car into the car park. And then we advance time by 5 hours to represent a 5-hour stay in the car park. So we didn't have to sit around and wait for 5 hours. And then we send the patron over to the payment machine to make the payment for this stay. And you'll notice that the calculated amount matches what we expected. And finally, we cause the vehicle to exit the car park.
The facilities for setting and advancing time, both real and simulated, are available both in the model interpreter we use for testing and the model compiler we used to deploy the client-server car park application. Recall our earlier discussion about when to use simulated time and when to use real time. Well, when demonstrating the car park with a real human in the loop, we have to use real time because the interactions involve timeouts for things like timely removal of the ticket from the entry stand, making payments at the pay machine. But we can use manipulation of the time base to skip over the uninteresting periods between interactions. How do you and the audience attack these problems? Please let us know in the chat.
The car park and payroll models contain examples of storing time values and date values using an epoch-based time system. They also contain examples of calculating durations and using those durations to calculate things like the value of a stay in a car park or the amount that goes onto a paycheck for a payroll. The test benches for these models manipulate the current time as seen by these applications. And they do this by setting the current time to an absolute value, and they also do it by advancing the time by an offset.
The test benches we built for both the car park and payroll applications leverage a modeled general purpose test framework that allows you to build a test bench containing simulated entities, both humans and peripherals, which can interact with the system that you are testing. This framework also makes it easy to build modeled test suites, which are comprised of collections of self-checking test cases which establish preconditions, inject stimuli, and compare expected and actual post-conditions.
For more information on any of the topics we've discussed, or if you want help adopting a model-driven development flow, please contact us.